Hi everybody, welcome back. We're going to be talking more about policy gradient methods today, and we're going to start off with a quick refresher understanding. All right, let's go ahead and go through these. So everybody said the last thing was false, which is correct. It is not guaranteed to converge. They're not guaranteed to converge to a global optima. They're just guaranteed to converge to a local optima of the policy gradient space. The first one is true. There are different ways to write this down, but in general what we're doing is we're going to be trying to take steps in the policy parameterization space. We're parameterizing our policies by theta, so that we're going to be trying to move in the direction of the log of the policy parameters times their value, the return you get from them. The second one is false. There's a bit of disagreement over this. So theta, because you can see from this first derivative, we are going to look at the direction of the derivative with respect to theta of the log of the policy parameters, but it's weighted by the return or weighted by the Q function. So whether we push it up or not will depend whether or not we're getting high rewards when we go in that direction. So this one is false. And this one is also true. That in general, what we're trying to do is we're trying to find parts of the policy space such that when we follow that policy, we visit states and actions which have higher estimated Q function or higher estimated rewards. Do you have a question? No, stretching. Okay. Great. All right. Okay, so last time we started talking about policy search, which was this idea of saying we're going to be directly trying to search in the policy parameterized by some theta. This could be a Gaussian policy class, this could be softmax, or this could be, as it will often be, a deep neural network. And what we're going to talk about today is we're going to get to finish off that part and then talk about more advanced policy gradient methods. And in particular today, we're going to cover at least the majority of PPO. So this should be enough for you to be making significant progress on homework 2. So in particular, what we're going to be covering is, we've talked last time a lot about likelihood ratio or score function policy gradients. We're going to talk more about the notion of a baseline and why introducing that is not going to incur any bias in the estimate of our gradient. We'll talk about alternative targets, and then we're going to talk about PPO. And again, just to remind ourselves, PPO is what they used in ChatGPT and a huge number of other application areas as well. So it's a really, really useful technique. All right, so let's just remind ourselves. We talked about how we can take a derivative with respect to the value of a particular policy. So this was the policy parameters. And we showed that it could look like this. And this was an unbiased estimate of the gradient, but it could be very noisy. In part because it looks something like our sort of Monte Carlo estimates that we saw before, because we're looking at these returns. And so we talked about a couple different fixes, or we started to talk about fixes to make it tractable. So one was to leverage the temporal structure, meaning that your reward on time step 3 can't depend on your actions after time step 3. And so we could use that to reduce the variance of our estimator. And now the next thing we're going to talk about, we started talking about this last time, is baseline. So as we talk about this, I think it's just useful to keep in mind throughout this that we're always trying to sort of converge as quickly as possible. So we want these estimates to be, of the gradient to be as low variance as possible, so we can try to be taking better steps in our policy space. Okay. All right, so let's look at the baseline. started talking about this before, and we said, well, when we are thinking about how to move our policy inside of the policy space, we want to think about not just how much reward we're getting, but really maybe how much reward we're getting relative to other things we could be doing. So we want to know how much better this policy is compared to other stuff. And I said you could introduce this baseline, B of ST, which was only a function of the state. So note, not a function of A, of theta or A. Now there's been other work, including from my lab, thinking about whether we can introduce baselines that may be a function of something beyond the state. But for today, we're just going to assume that it's only a function of the state. And what we're going to prove now is that for any choice of the baseline, as long as it's only a function of the state, this gradient estimator is unbiased, which means that we could introduce this here and we're not changing, on average, what the gradient estimator is. And a near optimal choice is going to be the expected return. Okay, so now we're going to, again, just be trying to think about how much better it's taking the actions under this current policy compared to other things we could do. So let's see, we're going to step through why adding a baseline does not incur any bias in our estimate of the gradient. So what we're going to do this is we're going to think about how our gradient comes together. Let's make sure I put these. Good. Okay, so we can think, so remember tau, here's our trajectories, and then this is our gradient. And what we want to, so the goal is to show this is equal to 0. Why is that? Because if we think about what this term was, this first term was an estimate, unbiased estimate of the gradient, and now we've subtracted off this term times this term. And we want to show that in expectation, subtracting off that term is 0, which means that we didn't introduce any bias. Okay, so let's just step through how that works. So the goal is to show this is 0, and we're just going to step through this. So our expectation is over tau. Tau's are our trajectories, so let's just write it out. We can write it out as the states we've seen up to a time step t plus the states that we see from that time step onwards. Okay, because that's like we're just writing out our full trajectory. So we can just think of our trajectory here as being, you know, S0 to t and A0 to t. Nice one. And that's just the full trajectory, so that's tau. And so we're just going to decompose this expectation. Okay, so we break this up. And after we've done that, we can notice, I can just make that, hold on. We can notice that we can pull one of the terms out. Okay. I'm going to pull this out because this is not a function of this future expectation. Okay, and I could pull that out there because it's just a function of the current state and it doesn't depend on the future states and the future actions that I take. All right, so that's what I did. And then next I'm going to notice that, well, this term here is only a function of the state and the action. It's not, again, a function of all the future actions and future states. So we can just rewrite that as expectation over the action t. All right, so what are we going to do next? The next thing we're going to do is I'm just going to write this out more fully. So I'll repeat this. So we've got our baseline here, ST, and we're going to write out what this expectation is. Okay, this is an expectation over the actions. What actions are we taking? We're exactly taking the actions according to our policy. Okay, so I've just rewritten what that expectation is. The expectation we're taking over actions is exactly the probability we take each action according to our current policy. Okay, but once we have that, we can play the likelihood ratio, or we can think of, what is this derivative? This derivative is equal to B of ST, sum over A. The derivative of log is just going to be the derivative of the things inside divided by, oops, I should have added, let me put a theta in here to make it clear that all of this is a function of my current theta. Okay. So I just took the derivative with respect to the log, but when we see that, we realize we can cross those out. So we can cross off this, we can cross off this, because that's the same. Okay, so now what do we have? We have the expectation over our states, B of st, sum over A, derivative. Remember, we're taking the derivative with respect to theta, pi of at st theta. Okay. So this is what this looks like so far. And now what I'm going to do is I'm going to switch the derivative and the sum. Okay. So I'm going to say this is B of st, derivative of theta, sum over A. Okay, why was that important? Because now, and let me just, that we know here that the sum over all actions we could take at this time step has to sum to 1, because that's true for any policy. So this has to equal 1, so which means we have B of st of the derivative of theta of 1, which is equal to 0, because that's a constant. Let me just show it here because it's more neat. Okay. So there's two there's two main insights for how we did this proof. The first was we thought about our expectation over all trajectories, and we broke it up to the part of the trajectory that happened before sort of the state of interest, the st, and the part that happened afterwards. After we did that, we showed that we could rewrite that expectation just in terms of at, because we didn't care about all the future stuff. This only depends on at and st. And then we take the derivative, and then we can see that we can switch these, and then that just becomes 1. And it's a constant that doesn't depend on theta, and so the derivative with respect to theta of it is 0. And so that is why introducing a baseline that only depends on the state does not introduce any bias, because an expectation, its value is 0. So that allows us to derive what we often call sort of a vanilla policy gradient method, which incorporates both the temporal structure and a baseline. And so the idea in this case is that we're going to collect a set of, we're going to take our current policy, which is parameterized by theta, we're going to roll it out a number of times, and then we go for sort of each time step t in each trajectory, we're going to compute the return, this is like our Monte Carlo estimate, and then we can compute the advantage estimate, which is we take that current return from that state till the end of the episode minus our baseline. And then, and someone asked me about this last time, generally we're going to change refitting the baseline each time. So we can re-estimate the baseline. Again, it doesn't matter what we pick for the baseline, it will always be unbiased, but there will be better or worse choices. So you can imagine if the baseline is 0, it will never make any difference. The goal is to hopefully have a baseline that's pretty informative and has a value close to the value of your policy. And so then we'll update the policy using our policy gradient estimate, which is a sum of these terms. Okay, so we're going to use all of these terms where we've got that derivative with respect to the log of the policy parameters times our advantage, and then repeat. So this is like a vanilla policy gradient algorithm. Yeah?
There is no discount factor in the return. Is that intentional as well?
Yeah, good question. So right now, so the question was, there's no discount factor. There's no discount factor right now because we're assuming we're in the fully episodic case, so we don't have to have a discount factor. You could certainly include one if you want to. Yeah, so for right now here, we don't have a discount factor. Now, one thing that you might think about when you're starting to look at this is to say, well, a lot of this feels like the Monte Carlo estimation that we did earlier in the class. We've been using these G estimators, this return, to estimate what is the performance of the policy from this time step to the end of the episode. But as you might imagine in this case, that generally is a pretty noisy estimate. Okay, so then the question is going to be, could we maybe do better? So there's sort of two places we could imagine, I guess there's two things here that we could imagine plugging in other choices for. There is what is the return of the current policy from a particular action till the end of the episode, and what is my general estimate of the performance in that state. So one thing you could imagine here is if we think back to Q functions and value functions, maybe we could plug those in instead of using the return and using a generic baseline. So you could plug in, instead of saying what is the return from this date and action to the end of the episode, you could imagine plugging in the Q value for the current policy from this date and action to the end of the episode. And we can either make gamma equal to 1 or not. We're going to generally assume, for now, assume episodic. So you can set gamma equal to 1. And the state value function could be a good baseline. And just to remember here, like on this slide, you can think of G as kind of being like a Q function and B as being a value function. So this would be an alternative we could do. Okay. So let's think about how we generally could sort of reduce variance. So what we've seen so far is we're mostly using Monte Carlo-like returns. Now let's see if we can do something better. So one thing we can do now is we're going to try to plug in and use things like state action values. And this is where the idea of actor-critic methods come in, which are also really popular in reinforcement learning. So the idea here is that we could reduce the variance of this estimate of the value function at a single ST from a single rollout by bootstrapping or doing function approximation at that point. So you could think back to like deep Q learning or something like that as a way for us to approximate what the value might be, or just general sort of deep learning for the value function. Okay. So when we do this, we end up with what is called actor-critic methods. The idea is that the actor is the policy. So the actor is the policy, often parameterized by theta, and the value function, or the state action value function, is the critic, and it's represented in V or a Q function. So that's why they're called actor-critic. Actor is our policy parameterization, critic is our state action value. And the great thing is that we can use both of those inside of a policy gradient algorithm. So you are constantly updating an estimate of the state action value, as well as having an explicit policy parameterization, and you use them together to hopefully increase the rate at which we learn to get a good policy. Now in this case, normally what we're doing here is we're gathering data using the policy, and then we're using that data to fit a critic. Okay, and the reason we call it a critic is because the critic is sort of trying to estimate the performance of an explicit representation of the performance of the policy. So the actor makes decisions and the critic says that's how good it was. So that's why it's called actor-critic. A3C is a pretty popular actor-critic method. There's quite a lot of others. So many of the reinforcement learning algorithms will end up being essentially actor-critic algorithms. And so it'll be useful to have both representations. So if you think of it, you'd have a sort of a deep neural network to represent your policy, and you'd have a deep neural network, a separate one. You could share parameters, but you don't have to represent your value function. All right, once we do that, we can think of rewriting our policy gradient formulas. So this was what we had before. We could approximate this now as saying, well, what if we just plugged in, instead of that return G, which is that sum over the rewards, we plugged in a Q function. And we plugged in a parameterized Q function with a parameter W. So these were our weights. So now just to highlight here, we're going to have these two sets of parameters, W and theta, theta for the policy, W for the value function. And if we let the baseline be an estimate of the V, then we can just directly write down sort of a state action advantage function, where we look at the difference between the Q and the V. And so now V is serving as our baseline. And I'll just highlight here that using the advantage function was one of the first things that I think there was, got best paper maybe in 2016, right after deep Q learning started coming out and people thought about these different adaptations. One of the things that was proposed is to think about trying to maximize with respect to advantages. But here we're going to be using that within a policy gradient approach. Okay. Now, one of the things you might wonder here is like, okay, well, we've got these extremes. On the one hand, you could have this Monte Carlo return of what is the value of the state in action that you get from starting that state in action and rolling out to the end of the episode. And the other is you could plug in a Q function. Now there might be some sort of blending between these two. So these are known as end-step estimators. So a critic in general doesn't have to pick sort of a temporal difference. A temporal difference in the way that we've seen it so far is normally, so this is, I'll just write down here, it's often, we've seen it as TD0, which means we have the immediate reward plus gamma times V of S prime. So in TD0, you think of your immediate reward, and then you plug in or bootstrap immediately when you say like, and I saw the next state, and I'm gonna plug in my value for that next state. So if you think back to our tree representation, it's like you see one actual observed return, and then you plug in your estimate. But in general, you could trade off between taking one step or taking 2 steps or 3 steps, and then plugging in your estimate of the return. So in particular, here's a number of different types of estimators you could look at. So you could have, let's call this R hat 1, which is you get your immediate reward, this is what we've seen before, plus gamma, then you bootstrap. A second one would be you take your next 2. Again, your gamma can be 1 or not, and then you plug in it. And sort of R hat infinity would be your normal Monte Carlo return, which is you don't do any bootstrapping, you just sum up all your rewards. And you can think of each of these as being estimates of your Q function. And then you could just get advantage estimators where you subtract off the V of your current state in each of those settings. So those are all things you could do. They're called n-step estimators, where n is sort of the number of time steps until you bootstrap. And one of the important things to think about is where you might want to trade off between these ones. So we'll do just to check your understanding now. If we think about introducing these type of blended estimators, how does bias and variance trade off? So why don't we go ahead and do that now. Can you select more than one? You should be able to. Does that work? Okay, good. I'll give you one more minute to think about it and put in your answer. And then there's a lot of variability in what people are saying. And so why don't you talk to your neighbor in a second? All right, maybe turn to a neighbor, compare what you got. What do you think about it? Yeah? You are subtracting the V function, but if you think back to Monte Carlo and TD methods, they have the same bias. Well, this is the question: are these both? Do these both have the same bias? So if you ignore subtracting off V for a second and just think of the first part of the estimate, Do you think the first one has higher bias or the second one?
Yeah, I don't know why it has high bias.
If you think back, the first one should be like the temporal difference method, and the second one should be like Monte Carlo. And remember, I guess I should be clear that these V's are all estimates, so they're not like converged.
So then the top one has higher bias.
Exactly.
And the second one has lower bias because of the actual value.
Exactly, yeah. And then what do you think that means for the variance?
I guess higher variance also is the top one because it's an estimate.
Close, yeah. So for the first one, you're totally right that it's got higher bias because you're immediately bootstrapping, but in general, it will have lower variance.
Okay. Oh, is that just generally a trade-off? Okay.
Yeah. Normally the Monte Carlo methods, because you're summing them out, they're normally totally unbiased, but they have lots of terms, so you could think of there's lots of stochasticity.
Oh, okay.
Yeah, and then the other way is normally don't.
I see. Okay. That makes sense.
Cool. All right, I'm going to ask if people, I'll turn this back. Yeah, I'm going to ask, did anybody change their mind after talking to someone? Okay, at least a few. Yep. All right. So I think one of the things too I just wanted to clarify here is that I find it I think it's often easiest to think about this without subtracting the V, because the V is the same in both of these. So you can just focus to understand which of them has high variance or high bias. You can just focus on the first things. And when you look at just the first things, it should remind you of Monte Carlo methods versus temporal difference methods. So the first one has low variance and high bias. Does somebody want to say why? So the first one, which looks kind of like a TD0 update. So this one has low variance. So A1, low variance, high bias. Does anyone want to share why that is?
Which is, sorry, it wasn't on the doc.
It wasn't, no, I was, yeah, just to clarify. Just to make sure, I'm going to explain what each of them have, but yes. Do you want to say in the back?
Yeah.
And remind me your name.
So I'm not entirely sure, but I think the intuition, at least when I was thinking about it, was that using the actual values of, like, for example, RT plus 1 is like more accurate versus like if you bootstrap very early, that's like more of an estimate. Like it's not as accurate.
Yeah, that's exactly right. So it's the same as in temporal difference methods. In general, it's a little misleading sometimes to look at these. Maybe I should put hats over all these next year. But all of these V's are just estimates. They're like given finite amounts of data and however many backups we've done, et cetera. V is an approximation, so this is an estimate. So this isn't true. And if it's not true, it's probably biased. So this is, in general, V will not be an unbiased estimator. It's just, and so this means that we're only using one point R from the true policy, and then we're immediately bootstrapping. So in general, this is going to be high bias or higher bias, but it's generally going to be pretty low variance. And the way to think about this is that each of the rewards in general are going to be from sort of a stochastic process, because you're like taking a series of steps, and then at each one you're going to sample a reward from there. So you only have kind of one really random thing here, and then one thing that is fixed. It might be wrong, but it's fixed. In contrast, this one, which looks like a Monte Carlo estimate, is going to have high variance because it's got all of these different rewards that are all being sampled from like a stochastic process. So if you think of it this way, like imagine it's something where like your robot can walk anywhere over the room, and under your policy, like your policy is, it can go in all of these different directions. Okay. But when you actually just execute one trajectory, you're just going to get one of those. And so its variance generally is enormous. And this might be true even if, like on average, you kind of have a trajectory like this or something. But so in general, this one is going to be really high variance, but it's generally going to be low or zero bias. Why is it low or zero bias? Because this actually is a return from the policy that you're executing. So in expectation, this really is equal to the value of that policy. So it's generally low or zero bias, but it can be really high variance. And so that should maybe give some intuition over, and we were just discussing this. In general, it's going to be, unfortunately, be a trade-off between low variance and low bias. And so often you're going to want things in terms of n. So this is, if that's the n step, and you want to sort of minimize your mean squared error, often you're going to end up wanting to do something where it's like a couple steps and then bootstrap to get a nice trade-off between bias and variance. And I think we'll probably talk a little bit more about that next week. Okay, so I'll just highlight this here, that this has low bias and high variance on this one. So this one has low variance and high bias, the other one is the opposite. All right, cool. Okay, so just to think about this, so when we are sort of thinking about these targets, we can go between these different ones. And then, oops, sorry, somehow these got copied. Okay, so these are all things that you can plug in. You can make different choices over whether you plug in these n-step methods or others. And then you can use this all as part of like your actor-critic policy gradient method. So now what we're gonna do, and I'll just make a slide to delete those slides. So now what we're gonna go into is more advanced policy gradient methods. Okay, so those are the basic ones, and they're kind of the backbone between all of the algorithms that we do now. But there's been a lot of interest in these types of methods and how do we scale them up and how do we make them better. Okay, and we'll talk about what we mean by better here. So we'll talk, so this is actually, we'll probably talk about some of this next week because I wanted to make sure that we got through the algorithm today so that you guys can have all the knowledge you need to be starting to do the implementation, and then we'll do more on the theory next week. So policy gradients so far, we've been talking about them being great and we know that they're used in some really important application areas. Why do we have to go beyond the methods that we just saw? Well, there's a couple different limitations to them. One is that the sample efficiency is generally poor, okay? And so that in general, you have to do many rollouts with the same policy. And in order to get a good estimate of the gradient, because you want a good estimate of the gradient, because otherwise when you take a step, you might get somewhere that's not as good or don't get to the place you want to as quickly. And the other, and we're going to see an example of this shortly, is that the distance in the parameter space doesn't necessarily equal the distance in the policy space. So this is a little bit weird of an idea, but the idea is that if you have a policy parameterization, whether it's like a deep neural network or others, there's some parameters in there, and when you change them, like when you change your theta, you're going to get a different policy out. But whether that is really smooth, like, oh, if I change theta, let's say theta is a scalar, so maybe theta is like 0.7. If I change it to 0.75, does that smoothly change how much more I take a particular action, or might it be really discontinuous? Like, might it suddenly say, like, oh, you were taking this action with 20% probability, and I changed theta a little bit, and now I'm like taking that action with 90% probability. The main idea here, and we'll see an example of this in a second, is this part may not be smooth, which means that even really small changes in your theta, in your policy parameterization, might actually lead to really big differences in how you're making decisions. Okay? So you could imagine your robot like picks up things one way, and then you change your theta a little bit, and suddenly it like drives off a cliff. Okay, not quite that extreme, but it's not clear that sort of as we smoothly take gradient steps in theta, if that's going to smoothly change our policy parameterization, our policy decisions. Okay, so let's look at those both. All right, sample efficiency. So what we've been seeing so far is the idea is that we take our policy, we roll it out one or more times, and then we take a gradient step. And we take one gradient step. And then we roll out our policy again. And in general, it'd be really nice to be able to take multiple gradient steps. But so far, we have not seen that. And it's called sort of on-policy expectation. So this is similar to kind of SARSA and other methods we've seen before, where like you're learning about a policy and its value by actually executing it. So the problem is, when we think about, let me just go back to here. When we think about doing these gradients, we've assumed that we've gotten trajectories from the policy and the theta that we're at right now, and then we use that data to take a step. So, we're at some point, here's our theta. We're at some point, and we estimate the gradient from that point. Okay, so we estimate it from trajectories that are generated under theta, and then we take a step. Now the problem is, if we now we might be here. And what we would like to do is to take another step before getting more data. But the problem is, we don't have, let's call this theta prime. What we have is we have data from theta. We don't have any data from theta prime. So a priori, it shouldn't be clear that we could take more than one step. We can take one step because we have data about theta, we estimate the gradient at that point. Now, we would like to just be able to continue to take gradient steps before we actually go out in the real world and gather more data. But it shouldn't be obvious how to do that yet. And so when we talk about policy gradient, right now we've been talking about sort of on-policy methods where we just try to estimate the gradient for the policy we just executed. So similar to SARSA. Now, so what we would like to be able to do is, so that's what we've been doing so far. We collect sample trajectories from the policy, then we form a sample estimate. It's pretty stable. We get our gradient, we take a step. We rinse and repeat. Another thing we could do, like thinking about Q-learning or others, is like, well, what if we could use that old data to estimate the gradient at some other theta, some other policy? Could we do that? This is known as off-policy estimates. This generally can start to be pretty unstable. We're going to think about different ways we could even do that. But we really would like that. We would like to be able to use our old data to take multiple gradient steps before we actually have to gather data. And you can imagine that might end up allowing us to be much more data efficient, so that the total amount of times we have to gather more data is much less. So we're going to think about a way today, and we'll talk more about this certainly over the next few weeks as well, of like how do we use our old data to essentially move faster in our parameter space. Okay. Here's the second big challenge. Okay, so in general, we're going to be doing sort of stochastic gradient ascent with some step size. Like we've repeatedly thought of there being some sort of learning rate or step size. One of the challenges, and this was important, you know, for deep Q learning, we thought about it even for like TD learning and stuff. What was the step size? How much do we update our estimate every time we get new data? Turns out it's much harder here. Now we saw before that under some like, you know, pretty loose requirements on the learning rate, we could guarantee, you know, at least in tabular cases, guarantee to converge, et cetera. Policy gradient methods are a little bit different. Here, the step size really matters. And if we take a step size that is really quite bad, we can collapse in our performance. Does anybody have an idea of why? Why does that happen? Why can we suddenly collapse? Mofa?
Might miss the optimal target and then go further.
Yeah, well, that is great. So let's look at an example. So remember, the way that we're getting our data is from our policy. If you overstep, so let's say we're trying to get to this point, you have a big learning rate, so we took big steps. You might now get to part of the space, which is really bad. Like really, really bad policies. By really bad policies, I mean they have really bad value functions. If you have really bad value functions and trajectories, which are visiting states and actions, which all have really bad reward, it's really hard to estimate a good gradient of where to go. In general, you might be in sort of like a really long plateau place, right? So this could be really long. And so the gradient here might be really hard to estimate of like, how do I get back to that local optima? In general, it's not going to be impossible, unless, you know, it's completely flat, but it might be really close to completely flat. And so that's a big problem, is that you don't necessarily know how large your step size should be. On the other hand, if you use really small step sizes, that's bad too, because then you're just, you know, each time your step size is basically determining how much you change your policy before you get new data. And so you would like to take as big of step sizes as possible that don't overstep and that allow you to quickly get to the optimal local optima. Now, you know, things like sort of atom-style optimizers, et cetera, help, but it won't necessarily solve the problem. And one of the challenges here is, you know, that we're only getting information about the states and actions that are visited under our policy. And you just might get to regions where there's very little information to estimate those gradients. Here's another challenge, and this relates to sort of that we're taking steps in the theta space, not directly in terms of the actions we take when we update our policy. Okay. So let's think about sort of a parameterization, which is a pretty simple parameterization. So this is it's a logistic function. This is like 1 over 1 plus e or something. Okay. So in this case, this is the parameterization. It's kind of, kind of like a softmax. You just have some probability of going to one action, and the rest of it probably goes to the other, and you've parameterized it with theta. So if theta is equal to 0, it's 50-50, like you'll take A1 or A2. If theta is equal to 2, you suddenly take A2 with much less. And if theta is equal to 4, you basically never take A2. And that's just because of how our relationship goes from theta to pi of A. Like in this parameterization, it's pretty extreme. So as we make sort of small, relatively small changes to theta, like I didn't make theta 1,000,000 or anything, I've basically shifted, even with sort of like 0 to 2 to 4, I've radically shifted how much of my probability mass goes onto A1. And that's just sort of just to illustrate this issue of smoothness. That is, I make what might be considered relatively small changes in my theta space that might make my policy near deterministic. And we know that if our policy is deterministic, we can't learn anything about other actions. So let me just make this a little smaller so you can see the question. So the challenge in this case is that step size can matter a lot in terms of efficiency. We don't necessarily know what the right step size is, and it may be hard for us to know how small changes in our parameter space relate to changes in the action distributions we actually follow. And so what we'd really like to do here is to actually come up with an update rule that doesn't sort of overchange the policy too quickly, but still allows us to make rapid progress. So we'd like to sort of move as far as we can in a way that we think is really ideally is going to just directly increase the value of our policy. Okay. And I guess I'll say, well, we'll see a bit more of that. I mean, and also ideally, we would like this all to be monotonic. We would like it so that if we think back to the policy improvement algorithms that we've seen before, policy improvement algorithms for the tabular case where we knew how the world worked had this great property that every time we updated our policy, we got a better policy or we were done. Now the world is much more complicated now. We've got, these sort of continuous parameterizations. We're not guaranteed to get to the optimal policy, but it would be really cool if we could still guarantee that we're going to just get sort of monotonic improvement unless we get to a local optima. And the things that I've shown you so far, don't necessarily have that property because they'll still converge to a local optima, but you might sort of overstep like we see here. So you might go over, you might be having monotonic improvement and then crash. And then you have to go back and forth. So we have not guaranteed monotonic improvement so far. But that would be really nice, and that could be important in a lot of real world domains. Like you could imagine, if you're using this for like healthcare applications, you would really like to have monotonic improvement and not suddenly kind of performance crash. All right. So let's think about how we might be able to get here. And you can think of a lot of this lecture as motivating the things that you're going to be doing in homework 2. All right, including the theory. So in general, what we'd like to have is we'd like to have an update step that uses all the data that we just got as efficiently as possible, and that takes steps that sort of respect this distance in the policy, like the decision space, as opposed to just smoothness in the parameter space. And in order to do that, we need to sort of understand how does the performance of two policies relate. So we have data from one policy, and we're considering trying to move to a new policy. And we'd really like to know, okay, given the data that I have from policy 1, what does it tell me about how good policy 2 might be? Because ideally, it would allow us to, policy 1's data would allow us to tell us which policy 2 I should move to next. All right. So this is what you're proving in homework 2. You're going to prove the performance difference lemma. And in the performance difference lemma, it allows us to relate the performance of one policy, the performance of one policy to the performance of another policy given data from one of the policies. Let me just state this out. So what does this say? This is, the value of one policy, policy 1, policy pi prime. I'm just using J here, but this is value. V is what you can think of this as just V. So what is that equal to? Okay, that is equal to the expectation over trajectories that are sampled using pi prime of, and again, if this is if finite, can use gamma equal to 1. Okay, we sum over the distribution of trajectories you could get if you followed policy pi 1 times the advantage under policy pi. Okay? So this part here is just equal to the difference between if you took an action minus, okay. But note here, because this expectation here is over pi prime, the way we're selecting these actions, I'll just write it out a little bit more. Imagine we have deterministic policies. So it's like we're thinking about the Q value if we first take an action according to policy pi prime and then follow policy pi for the rest of time versus what we would have gotten if we just followed policy pi the whole time. So you can think of it as sort of like breaking down the difference in the value between two policies into a series of small differences of like, well, how much gain would I have gotten at this state if I had taken pi prime's action instead of the one I actually took? Okay, what about here? And then you kind of like want to sum up all those additions. Like every day I'm happier because I went to Stanford instead of Harvard. And I just add up all of those and that tells me over the course of my whole career how much happier I will have been. Hypothetically. Okay, so this here is over trajectories. Now we're going to make a transformation and move it into state action distributions. Okay, because what this is going to be here, so now this was over trajectories. We're going to rewrite this just in terms of state action distributions. Okay, what we're going to say is, all right, as we think about adding up all these advantages, what I'm going to do is I'm going to cluster together all the advantages that have to do with the same state. So I think of there as being a distribution over states I might reach and actions I might take under policy pi prime. So if I just follow this policy, I'm going to visit some states, and I'm just going to think about what is the advantage in each of those states weighed by how frequently I visit them. So we're sort of transforming things from thinking of it as being like trajectories and thinking about weighting over time steps to weighting over a finite set or, a space of states and actions. And so we'll have a distribution, it might be like I visit state 1 half the time, I visit state 7 only, 1 in 10,000 times. So this allows us to reweight the advantages. What does this distribution look like? This looks like the following. Essentially, you just think of what is so here we're allowing us to have discount factors because we're looking for the infinite case, but you can adjust this. What this is just saying is that, well, my sort of weighted distribution for state S is equal to, well, how likely was I to be in state S on time step 1 under that policy? Well, how likely was I to be in state S in time step 2 under that policy? What if I was in time step 3? And so you just sum up all of those. And as you could imagine, in the infinite horizon case, you're gonna, those could easily go to infinity, particularly if you have states you can visit a lot. And so the discount factor here makes sure this becomes a distribution. So we want this still to be normalized. And then similarly, this is also with respect to taking the actions under pi prime. So you'll be proving this in the homework, but we'll see how this can be helpful. Okay, so why are we making you do this? So the nice thing is it's going to define the performance of pi prime in terms of advantages from pi. Okay, so that seems good because we're like, well, we have an existing policy, but the problem is this still requires trajectories sampled from pi prime. So you could think of pi as potentially being the policy we have right now, and maybe we can estimate the Q function for it, we can estimate its advantages. And now we want to figure out how good would be this new policy we might take. But the problem is we don't have any trajectories from the new policy, we only have data from the old policy. Okay, so we really want to get to something where we can estimate how good is pi prime using data only from pi. That's our goal. So like our goal, estimate J pi prime only from data from pi. So you can think of pi prime as the new policy. So what we really want to do is sort of take a step so that like our new policy is the best one we could get to in terms of its improvement over the previous policy. And we want to be able to do that by only using an estimate from our old data. And it shouldn't be clear yet how we could do that. Like this is looking promising, but we still seem like we need data. So this is still data for the new policy. So let's look at it from a different angle. So this thing d pi of s is a distribution over states. It's a discounted future state distribution. And we're going to use that to sort of rewrite the relative performance, policy performance identity. So why is this relative? It's because it's with respect to the performance of our current policy. So that's why we have a subtraction there. Okay. We're going to rewrite that there. Let me see if I have it. Okay, yeah, so I'm going to step through this. So what we can do at this point is we can rewrite it as follows. So right now, remember, this is in kind of like the time or the trajectory notation. Okay. So I'm going to again rewrite this so that I'm going to move it into the state action representation. So instead of thinking about it as trajectories, I'm going to think about it as what's the distribution over states and actions that I'm visiting. Okay, so I'm going to write it as follows. 1 over 1 minus gamma sum over, I'll just write as the expectation. Expectation over S prime according to pi prime according to pi prime of E advantage. Okay, under, let me actually write it this way. Okay, what have I done there? So this should look pretty similar to the previous slide. What I've said is, okay, this is the discounted future state distribution. I saw on the previous slide that I could rewrite this expression as 1 over 1 minus gamma E times S times this D times A. So that's what I'm doing now. So I've rewritten it in terms of this state action distribution. Okay, and this is where I'm in this problematic case that I've got the wrong, oops, let me make sure I put a quote there. So this is, just to be really clear, this is over pi prime. Okay, so this is all with respect to the new policy. So now I'm going to note the following. Okay, so what does this look like? This looks like it's 1 over 1 minus gamma, the expectation over S prime sampled according to D pi prime. And then what is this expectation? So this is going to be sum over A pi of A given S pi prime. Oh, that's horrible notation. Let's try this again. Okay, that's what this means. Like I'm taking an expectation for each of the states. I'm taking an expectation with respect here. Let me just try to make this neat. There we go. Okay. So I'm saying, imagine I sample states from my d pi prime distribution. How do I do this expectation over A sampled from pi prime? Well, I just sum over all the actions, look at the probability of me taking that action for that state under pi prime times my advantage. Okay. So now the key thing we're going to do is we're going to try to change this so that we're using we're going to try to get to a point where we only need data from pi. Okay, so the first thing we're going to do here is we're just going to rewrite this, and I'm going to multiply and divide by the same thing. Okay, so I'm going to say this is pi prime of A given S divided by pi of A given S times pi of A given S. Okay, I have not done anything except for I've multiplied and divided by the same thing. Why did I do that? Well, the good thing is I know how to get samples from this. I have samples from this. This is from my old data. This is from the actual policy that I took before. Okay, so what this says, I can write this as, I've got 1 over 1 minus gamma, E of S according to D pi prime. And then I have this expectation over A sampled according to pi, not pi prime, of my reweighted advantages. Okay, and what do I reweigh them by? I reweigh them exactly by the probability I take that action under the new policy versus the old policy. And that's okay, because I'm going to assume that I have access to the policy parameterization of the new policy. I'm just trying to figure out how good it is. I don't have samples from it, but if you tell me, hey, this is the action you took in that state, I can say, oh, okay, well, that's how likely I would have taken that under my new policy. So I can do that reweighting. And this is an instance of something called importance sampling, and we're going to see a lot more about that soon. But so this is the first step I can do. So this is great, right? Because now I don't need to have samples from actions taken by my new policy, I can just reweight the data I already have. So that's super cool. But there's a problem, okay? This is still pi prime. So I still don't have any data over states from my pi prime, okay? All right, so this is that just written out more neatly. We'll see a lot more on that in the future. Okay, but we still have this big problem because we don't have any states from pi prime. We have data from pi. Okay, so what are we going to do about that? Well, we're just going to ignore it. Always an option. So we're just going to ignore that and proceed. And this is what is going to happen in the rest of the class. For the rest of this lecture, we're just going to pretend that those states are the same. Now, as you might imagine, that is going to slightly induce some error in my estimate. When might that be bad? Well, it might be really bad, right, if the two policies would actually visit totally different parts of the state space. But if they visit things that are really close, maybe it's not going to be that bad. Okay, so let's imagine that you have, policy 1, and it goes, this is your robot, and it goes to most of this part of the space, and then you change your policy, and maybe it also goes to that part of the space, and it goes a little over here too, but there's quite a bit of overlap. Okay, the places where it would be bad is something like, if your policy goes like this, your new policy, and then there's like no overlap in your state space. So it's going to turn out that if pi and pi prime are close, and we're going to find what we mean by close, then this is actually not a bad approximation. It's not perfect, it's not too bad. So in the paper, they prove that we can bound how bad this approximation is. Okay? So in general, we're going to define this to be L, mass script L of pi with respect to pi prime. If this was perfect, this thing would be 0 because this would exactly equal this difference. So this minus this would be, these two things would exactly be 0. But what it turns out is that how far off this approximation is depends, bless you, on the KL divergence in the policies. Okay, and I'll define what KL divergence is in a second. So in particular, it depends on the KL divergence with respect to, let me just undo that so I can just do this part. With respect to states, if you were sampling them according to d pi. Now d pi is good because d pi is the actual discounted states that we visit under our current policy. That means we actually have data about it. So I always like to work in my lab, we always try to instantiate our theoretical bounds because I feel like it's super informative to be like, oh, is this like, 10 to the 10 or is this like 0.5? And one of the big questions often that comes up when we try to do this is that sometimes you can't instantiate your bounds at all because it'll depend on constants you don't know. So like it's a beautiful theorem, but like you can't even check how big it is. The nice thing about this is like it's checkable. At least this part is, right? Because you can look at your actual trajectories from your current policy, and if you have a new policy pi prime, you can see and evaluate what your KL divergence will be. So this is actually evaluatable. So we'll see. Okay, and then also.
What is C and what's its value?
So C is a constant.
Any information about its value?
No, I will. We're not going to need it for now, but in the paper you can read about sort of exactly what that is. Yes, good question though. Okay, let's see what KL divergence is. So what this says is just at a high level is that this approximation is not totally insane. If the policies are close, in fact, this is going to be a pretty good approximation. So as we're going to see, this is tight if the policies are identical, which is exactly where you'd expect this to be tight. So if your two policies are identical, their difference should be 0, and this bound would tell you it's 0. All right, what is KL divergence? Some of you guys might have seen this before, but in case, some people might be new. So what KL divergence allows us to do is to compare two probability distributions. So in our case, what this is going to be is over actions we will take. So like, pi of A given S versus pi of A given S. So both of these are probability distributions that sum to 1 for a particular state. And so what in our case, what we would be summing over here, x would be A. So we'd be summing over all of these. If you have the same probability distribution, the KL divergence is 0, otherwise it's strictly positive. It's good to know it's not symmetric because we've made a choice here in the ordering. So these are good properties to know about. It comes up all the time in reinforcement learning. So in our case, we can look at, for a particular state S, what is the KL divergence in what the policies would do for that particular state. So that's what we've got there. So it says, essentially, like how different are the actions you would take? Now, why is this good? Well, we've been spending some time saying, hey, we really don't want to think just about how close we are in theta space. We really want to get to thinking about how different are our actual policies, like how different are the actual decisions we make in particular states. And the nice thing is what this bound says, is that the difference between two policies is not just about how close you are in some parameter space. It's really about how different are the decisions you'd make in all the states you'd reach under your current state distribution. And so if you'd make all the same decisions in the states you're already reaching, your policy value is going to be really similar. If you would make very different decisions, then your policy value might be really different because you sort of go off and explore really different parts of the state space. Okay. So this is really elegant. And now we have something where we can just use our old data. So we have our old data. We can use it to estimate what the performance improvement would be if we try to get to a new policy. And so what you might imagine in this case is you could use to sort of search over or decide which new policy to try. Okay? This allows you to compute it for lots of different pi prime. It doesn't just have to be the pi prime for one gradient step. It says, in general, even outside of policy gradient methods, you can evaluate the value of changing your policy to pi prime with respect to your current performance by this expression. And this will be more or less tight depending on how different your policy is at making decisions in states that you would currently reach. Okay. And we'll talk more about this. We haven't talked about this yet, so we will talk about. Okay. This also relates to some really nice literature from kind of the last 20 years of thinking about how do we do monotonic policy improvement in sort of policy gradient methods and policy search methods. It also relates to the notion of a trust region, which is this idea of how, when you're changing your policy, how far can you go and still sort of trust the performance of it and trust you can get improvement. So there's a bunch of different nice papers related to this. Okay, let's talk about the algorithm. Proximal policy optimization is going to be inspired by all the things that we just talked about. So what we want to do is it wants to be able to take multiple gradient steps, and it wants to be able to do this in a way so that we don't overstep. We try to focus on policy parameterization in terms of the actual decisions that we make. So there are two different variants. One is it solves an unconstrained optimization problem where it uses this approximation. So that's the approximation we had on the previous slides. I'll just write it down from prior slides, where we use data from the current policy and we kind of add up these weighted advantage functions. So what it says is, well, the thing you want to do is you want to pick the policy that maximizes our estimated difference subject to a constraint on the KL divergence, because it's realizing that L approximation is going to get worse and worse as the KL divergence gets really large. So it's sort of directly incorporating this bound. So it's thinking like, okay, I want to think about what this is, but then I also have to consider the fact that my estimate might be off by as much of this sort of square root KL. So you really want to sort of improve with respect to something that considers both of those. Right, so this is one version of policy. This is not the way most people do PPO. We'll see the other really common one, but it's a nice baseline to know about. And here, when we think about what that KL is, as you might have noticed, KL is defined for a single state. So for a single state, we can say what is the distribution over actions I'd take in one policy versus another. But of course, we have lots of states. And so what we can do here is we can take an expectation over the KL, over all the states we'd visit. And that was part of the theoretical bound too. Another really important thing you can see here is this weighting. This weighting between trying to optimize kind of this policy improvement while respecting this kind of KL penalty. And you can change this over each iteration to kind of approximately satisfy the KL divergence constraint. So this does not guarantee that you will. This does not guarantee that you're going to get monotonic improvement, but it's trying to get towards that. Okay, so let's see how that works. So this is the algorithm. What it does is you can compute the advantages using any advantage estimation algorithm. You compute your policy update, and you can do case steps with that. So the nice thing is that you can use your old data here, and you can take multiple gradient steps. After you do this, you can also check if your KL divergence for your new resulting policy is large. If it is, then you may increase the penalty. If it's small, you can decrease the penalty. And that just allows us to sort of trade off between how much we're paying attention to this KL divergence constraint versus not. And as I noted here, you might violate the KL constraints, but most of them, they don't empirically. Okay, this is one reasonable thing to do based on everything we've seen. Now we're going to see something else which is inspired by that, and it's a much more common thing to do, which is, well, let me just highlight here. Multiple gradient steps is really good. So this is, one of the benefits is that we're not just taking a single gradient step, we're taking multiple. So just to really highlight that. All right, what is the other thing we want to do here? We haven't talked about natural gradients, but for any of you that are familiar with these, they're another way to try to think about taking gradient steps. We're not going to talk about that for now. So the other thing we could do is a clipped objective. So what we're going to look at in this case is, remember how we talked about we had this kind of ratio between, this is what we're using to weight our advantage function, was the difference between how likely you were to take that action under our old policy versus our new, and we were using it to weight our advantage function. What the clipping does is it says, well, I don't want this to get too high or too low. Okay, this could become really high or really low when my policies are really different. If my policy is really, you can imagine that if my policy puts a really low probability on something that the current policy puts high probability on, this ratio here is going to go towards, this R is going to go to about 0. And if this puts very high, let's say this is 1, and this puts very low probability on that, this could be extremely large. This could be like 10 to the 6. This could be very, very large. And both of those are being used to weight the advantage function, right? So your advantage function could be getting shrunk towards 0, or it could be getting blown up by a factor of, say, 10 to the 6th, if you have a big difference in the actions you would take under one policy versus another. And in general, we don't like things where, like, we're thinking of policy gradients where we might have terms that are exploding or vanishing. And that's part of the point of the KL divergence constraint, is to say you want your policies to stay close. So the clipping is sort of inspired by this general idea, but says, well, maybe something similar we can do is we're just going to clip. We're just going to say you can't have weighted advantage terms that are going towards infinity or minus infinity or 0. And so if this ratio is too extreme, I'm just going to clip it. I'm going to not allow it to be less than 1 minus epsilon or greater than 1 plus epsilon. And epsilon is just a hyperparameter. And essentially, it's sort of meaning that your policy might change further than that, but that's not going to benefit your loss function. So this, again, is going to sort of constrain your policy class to stay within this kind of region for which it's making similar decisions. So we're still really focusing on what actions are we actually taking. Are we taking similar actions in these states as we would be normally, regardless of how much my theta is changing? Okay. And then you just do your policy update by taking an argmax over this. So this is your clipped objective function. All right, so let's see how this works. Let's think about what it's doing. So we'll do a quick check your understanding. So this shows you what L-clip does. This is L-clip as well. And what I'd like you to think about is, what does this look like depending on the advantage function? So let me just write it down. L-clip. Okay, so this is R. So on the x-axis is R, and then on the y-axis is L-clip. And what this is asking you to think about, this is from their paper, is to think about what does clipping do in terms of your sort of loss. And so I'd like you to think about, in this case, which of these two, if either, match whether the advantage function is positive or the advantage function is negative. So A here is the advantage. Let me just make that clear. A is equal to the advantage. So just think of this for a single term. Consider for one term. Okay, so just this part. Okay, so just for one single RTA, what is happening here? And just to be clear here, what we're doing in this case is we're taking the minimum between the normal thing we do, which is this reweighted advantage function, times a clip of the R times the advantage function. And feel free to flip back and forth or play with numbers, just to sort of get some intuition of what is this doing to our, our loss function. Or I shouldn't say loss, our objective function in this case, because we're trying to take the argmax of it. So we're thinking of this as sort of an approximation of how much is our policy going to improve when we change our theta. And so we're going to want to take a max of this over with respect to a new policy theta. And we want to think about this as sort of bounding what that new performance benefit could be. And how does that vary with respect to the advantage? All right, nobody thinks it depends on the value of E, which is correct. So this is does not depend on the value of E. I want you to turn to your neighbor and see if you got the same thing. Oh, cool. It looks like talking converged most people, which is great. So does someone want, so the first one is correct. So this is A greater than 0. This is A less than 0. Does someone want to explain why? Most of you that voted got it right.
Well, it is quite simple because it's simply like coefficient to the value, so it has a positive slope and it is positive, and negative slope and it's negative.
Yeah, so if we just focus on this for a being equal to greater than 0, what will happen is as that ratio r gets higher and higher and higher, you'll just linearly go up because it's just something between 0 and 1 that's getting larger and larger. R can never be negative, so that's just useful to see in this case. So as it's getting larger and larger, it's just going to increase your L-clip value, but at some point you're going to run up against this part. And so at this part, you're going to clip it, and you can't get higher anymore. Remember, in general, we're always trying to maximize L-clip. In this case, when the advantage is negative, you're trying to sort of reduce the amount of probability mass you put on that action, because you don't want to take that anymore. Like, oh, I got a negative advantage, so I need to stop doing that. So essentially, you want to be changing your policy in the opposite direction. You'd really like to be able to push R all the way to 0 and say, I never want to do that action again. Like, it gave me a negative advantage. But you can't do that because that might change, radically change your policy. And so once you get to 1 minus epsilon, you cap it, and you can't further shrink it to 0. Great. Okay, so, and another way to see this is from the paper is like you can think about sort of these different types of constraints and different clipping, and essentially, again, it's sort of like making the objective pessimistic as you get really far from theta. Now, just in the last couple of minutes, I want to make sure to show some plots. So this is just the same algorithm, but where we're doing clipping. I will just note here that next week, so next time, we'll discuss. Next time we're going to discuss the choice of A further. Just like what we saw earlier today, you can do n-step estimators, etc. And you can do what's called generalized advantage estimation. You don't need to know that for this. We won't cover that for today, but we'll cover it more next week. So just to note, there's some additional choices here. But let's just look at sort of what the performance is. So at this point, TRPO and some other algorithms were out there, and they have the PPO clipping in purple. This is a number of different Mojoko domains, similar to Mojoko domains you're going to be working with. And what you can see here is that in general, so TRPO has this trust region idea, and it's similar in some ways to what they're doing in PPO, but trust region policy optimization is quite a bit more complicated. And what you can see here is that like this light purple, which is PPO, this is the number of steps, is generally doing just much better than these other ones. So they're not claiming they're going to get to a better optima. They're just saying we're going to be able to get there much faster with much less data. And in some of these cases, this is really an enormous performance improvement for the same amount of data. So this is one of the reasons why it became extremely popular. It is a pretty simple algorithm to implement, and it has extremely good performance in many cases. Now, I do just want to, you can go to the original paper, Proximal Policy Optimization Algorithms, or go to the blog post from 2017. I do think one thing that's good to know, and really throughout much of RL recent history, is to also understand what are the implementation details. So this is optional, you don't have to read it, but there was a nice paper that followed up from this work, because again, PPO has been hugely influential, from some colleagues at MIT that said, well, really, which of these things are most important? Because in general, in these algorithms, there will be these things, but then there's also some hyperparameters or, architecture choices, et cetera. And so knowing how these choices are made often do make a big difference in reality. And so that's always good to know. It's whether or not, is it an algorithmic improvement, or are there additional things that we're not treating as part of the algorithm, but actually are really important for practical performance. So you should know everything now that you need to for making good progress on homework 2. And we'll continue to discuss this next week. Thanks.